Hello, Chetan.
Yes, sir. Shall we resume, sir?
Okay.
Yeah, fine, sir. We can resume, sir.
Okay, thank you, thank you. Once again, I welcome you all to the second session of our discussion. In this session, okay, I will focus on the two more parametric tests, that is independent sample with matched pairs and the analysis of variance as a continuation of testing the mean values. So for more than three or more than three populations. And the earlier example of that comparing the dividend yield between NASDAQ and New York Stock Exchange, there we have assumed that, and also it is true in real, is that the prices of those two are independent, or the dividend yield of those two stock markets are independent. They are not related. So hence earlier we have used independent sample test or independent two sample t test, better to say. But in some cases, the variable which we have chosen is dependent. For example, the effect of a particular policy before and after. For example, the effect of COVID-19 on any sector of the economy or any economic variable in general. Now, to assess or to measure the impact of that COVID-19 on any economic variable, then your analysis is before COVID-19, after COVID-19. Or if you want to measure the impact of GST demonetization, before demonetization, after demonetization, or pre-demonetization, post-demonetization, before LPG, after LPG, before 2008 financial crisis, after 8 financial crisis. So now, actually, you have selected a single variable, and you are comparing that single variable before and after. For example, if you take GST, the tax collections before GST and after GST. Tax collection is a single variable, but you are comparing that variable in the two periods. Hence, you should have to treat that as a separate variables, and you should have to test whether there is a difference in the value of tax collections before GST and after GST. So if you take, for example, the impact of Corona on GDP of India quarterly, so then before, say, COVID-19 and after COVID-19, or investments, or whatever it is, investment or import or exports of India before and after. In all these cases, you have to use this matched pair test or dependent sample test, dependent samples test. And the idea behind this matched pair test for calculations is that you have to take the difference between the pairs of the values. That is, you have, for example, 5 years before, 5 years after, 10 years before, 10 years after that particular variable. Now you should have to take the difference between these two. That difference is known as DI. It is the difference in the selected variable before and after. Before and after, that is DI. And the formula, okay, to test this type of hypothesis, that means there is no difference in GST before and after, tax collections before GST and after GST. That becomes your null hypothesis. Alternative hypothesis, you can whatever you can state. So there is a decline or there is an increase in GST. That left to you as a researcher, as you can expect on decline and test it. So hence the T, again you have to use your T test, but the form of the T test is different, because earlier you have noted that it is y bar, x bar minus y bar minus mu1 minus mu2 divided by whole square root of sigma square 1 by n1 plus sigma square 2 by n2 square root for that. That was the formula which was used in case of two independent sample T test. But whereas in this case, it is a simple formula where d bar is, earlier I have noted that It is the mean of the difference between pre and post period of the selected variable subtracted from your hypothesized value. Always our hypothesized value in case of this and also in all other hypotheses is no difference. So hence it is d bar by standard deviation of d by root n. So by using this, you have to test your hypothesis. If this calculated value by solving this problem or solving this equation or formula is greater than the table value of the t, you have to reject your null hypothesis of no difference. So otherwise do not reject. So the hypothesis testing is as usual. That is, if this calculated value is greater than the table value, reject your null hypothesis. Otherwise do not reject your null hypothesis. Even in case of this paired sample test, you can have one-sided test or two-sided test. So if it is two-sided test means your alternative hypothesis, there is a difference. In case of one-sided test, greater than the pre or lesser than the pre. So that is one-sided. That becomes one-sided test. That's why one-sided test is related to the test of your hypothesis claimed by you is greater or lesser. Okay, so even in case of this paired test, you can use all these three types of lower tail, upper tail, or two-tail test. So here we have one example related to customers, that is the salesman's customer service related training workshop. Because probably this type of paired t-test is much used in education research work, because they have new methods of teaching and so on, new designs and so on. Before and after kind of such analysis is much used in this. And also in psychology, of course, they much use of this paired test, because they are testing the various aspects in psychology before and after. So even economics, as just earlier I told you that wherever you come across or your hypothesis is to test the variable and its difference before and after, pre and post, in all those circumstances or contexts, okay, you can make use this paired sample t-test. Here in example is, assume you send a sales people to customer service training workshop. Say workshop has been conducted and it is related to customer service. As the training made difference in the number of the complaints, you collect the following data. That is, now after training, okay, and before training, the complaints by the customers, is there any improvement in the customer service by the salespersons? If there is an improvement in the customer service by the salesperson, then your training work is positively influence on them. If it is not, so that is not worth. The training which you have given to that salesperson is not worth, because there is no difference in the customer service opined by the perception of the customers. So that's why here for this the data is the number of the complaints on the few salespersons. For example, 5 salespersons before the training and after the training. Okay, it is the number of the complaints against the salespersons before and after. Then the process is you have to take the difference between these two. That's why 6 minus 4 is minus 2, 20 minus 6 is minus 14, and so on. You have to sum this, and you should have to take a mean for this. So that's why 21 divided by 5, it is 4.2 minus, and you should have to calculate the standard deviation for this. The standard deviation for this mean difference is 5.67, and you have to use these two values in that formula. The formula earlier we have noted that this is d bar is for minus 4.2. The standard deviation is 5 point something divided by n. That gives you a value. If that value is statistically significant, so you come to conclude that yes, there is an improvement in the customer service by the salesperson after this training, or the number of the complaints decreased because of attending that workshop or the training workshop. So these are the policy aspects or the conclusions that can be drawn by this one. Okay. So as earlier I told you, like it is a marketing related example. In case of economics, so as earlier I told you that the impact of LPG on particular, or impact of 2008 financial crisis, or GST of government of India, or the recent one is COVID-19. So by analyzing all this in a simple way, comparing your selected variable before after, you can use this matched pair test. So this is about the matched pair test. So thus far we have discussed related to the two sample mean test. In case of two sample mean test or the two population mean test, we have to choose two or one among the two. The one is independent sample mean test and the dependent or matched pair test. Okay. In case of independent sample mean test, if the variables are selected by you or independent, you have to use the independent sample test. If the variables are selected by you or dependent like pre and post or so on, you have to use matched pair test. And the procedure is same. That means if your calculated value of the t is greater than the table value, you have to reject your null hypothesis. Otherwise, do not reject your null hypothesis. Okay, these are the things thus far we were noted about the two population mean test. Okay, so then let us continue our discussion related to the extension of the same. We have started with a parametric test of mean test with a single sample mean or single population mean. Then we have included one more to that. That is two population means. Now three are more than three population means. So which means now we are comparing the means of different groups of populations. Three are more than three groups. Three are more than three categories. So then we have to use the analysis of variance. Whether the populations have equal means or not. So let us take one example. For example, say one company has three plants in three different places. One is in Bangalore, other one is in Mysore, third one is Hubli. Okay, now it has to assess the production efficiency of that particular firm in terms of the number of the production unit by the machines. So by the machines or by the total company or the plant itself in a particular period, 1 hour. So 1 hour. So that has been collected, for example, from the three plants. That is the units of production in plant 1, plant 2, and plant 3. Whether all three units have producing the same amount of units or not. What the company has to expect? The company has to expect, or the company has to say, identify or to determine, or the claim is there is no difference in the productive efficiency of those two companies. That is the machines or the operating system in that particular company, or these three plants. Sorry, three plants are one and the same. So to test this, it has to collect the data from all these three plants, and it has to calculate the mean values and compare the mean values of these three populations. And if these three population mean values are one and the same, so then there is no difference. Otherwise, there is a difference. If there is a difference exists, then the policy option is, or the action that has to be taken by that particular company is that has to be corrected. That has to be corrected. So like this, we have several such examples in practice. So, and also, for example, in case of an agricultural economics or agronomics, so that is the output produced by the farmer, okay, are the different farmers in three plants for the same crop, paddy crop in one group of farmers, paddy crop by other group of farmers, paddy crop by third group of farmers. Whether the yield of this paddy is same between these three crops or not, we have to use this testing of equality of the means for more than three populations. So, or in other words, more specifically, so that is whether there is any difference. Is there any difference in the paddy crop among the three groups of people using the three different kinds of seeds, using different kinds of pesticides, using three different kinds of fertilizers, or due to because of the fertility of the soil, color of the soil, because color of the soil, fertility of the soil, the type of the seed they use, then the fertilizers they use, the pesticide they use. So all these affect on the average yield of a particular crop. So of course, if you take all these variables, so the problem becomes complex. So in terms of analysis of variance because you have a variation, deviations, difference in the crop yield due to because of several variables. So if the crop yield is varies or not because of seed, it is called as one-way analysis of variance. So is there variation or difference in the mean yield, average yield of paddy because of fertilizer along with the seed? Then two-way mean as a two-way variance. So if you include one more variable, three-way analysis of variance. So we can extend this, but now for our simplicity, we here say fix our analysis or constrain our analysis to only one-way analysis of variance. That is the variation in the mean value of your selected variable because of only one factor. So, and of course, in agronomics and especially in agriculture research, this tool is much used and they are called it as factorial analysis, factorial experiments, factorial designs they are called, factorial design, factorial experiments and so on. But they are nothing but so use of this analysis of variance for those things. So actually they are calling it as treatments. So that is giving a treatment to a thing, whether it is changed or not. So even this analysis of variance is also much used in medical science, medical research. So that is for testing before and after type of treatment into kind of analysis. We have three groups. So in case of analysis of variance, that's why analysis of variance as a tool for testing equality of the means for three or more than three populations, which is generally called in statistics as equality of the k population means. Okay, this analysis of variance is used as a tool for that purpose, and now we have a brief discussion on this. As just we have noted that this analysis of variance can be used to test a hypothesis of equality of three or more than three population mean values. And we can obtain the data to conduct this type of hypothesis testing either from observational studies or from experimental studies. That's why I have told you that in case of agricultural economics, so they conduct experiments. So based on that experiments, they derive the data and use that data for this analysis, and hence they are called as the experimental design, factorial designs. But whereas in case of our economics, whereas in case of in management, whereas in case of commerce, and most of in case of social sciences in general, okay, our analysis are obtaining data only through the observations. So hence, of course, it is the data might be come from observational studies or from experimental studies. So by having the data from either observational studies or from experimental studies, so our null hypothesis is mu1 is equal to mu2 is equal to mu3 and so on is equal to mu k. That means there is no difference in mean values of that particular variable among the populations. Alternative hypothesis is not all populations are equal mean. That means there is a difference in the population means, or at least one population mean is differs from other populations. Okay, at least one mean is differs. This is the alternative hypothesis. The same is of course given here, and if the null hypothesis is rejected, we cannot conclude that all population means are different. So hence the null hypothesis rejection means that at least two population mean values are different values. So because you have too many populations, 5 populations, out of that 5 populations, mean values of the 3 populations might be same, but the 2 population might be different. That's why you are always bear in your mind in stating alternative hypothesis of this analysis of variance as not equal, but as at least one population mean or at least 2 population means is different from other population means as to be stated as your alternative hypothesis. Then what do you mean this and the sampling distribution? And this also several assumptions. Yes, earlier we have noted that all these 3 or more than 3 populations follows the normal distribution. So that's why here we have one one diagrammatical representation is this. Here the population mean values are closer because the true population is mu. The sample mean values are x bar 1, x bar 2, and x bar 3, and they are very closer to here when the populate these. In this case, the null hypothesis is correct. Null hypothesis is true because they are very close. Though there is a difference, this difference is not statistically significant. In this case, your null hypothesis is true. But whereas in this case, so the populations, the means, the sample means are coming from 3 separate populations. So if the means of your sample are coming from the 3 separate populations, then they are not close to each other. Since they are not close to each other, so there is a statistically significant difference exists between those 3 populations mean values. Hence, the null hypothesis is true. So that's why. What do we mean by null hypothesis is true in case of analysis of variance? You have a single population, all the 3 samples are coming from the same population, hence the means are identical. So if the mean values are coming from the different populations, sample means mean. Okay, the sample means are coming from the different populations. Naturally, the sample mean values are not equal, and hence your null hypothesis is true. So this is just the diagrammatical distributional type of depiction of that null and alternative hypothesis in case of analysis of variance. Okay, this is a background to that analysis of variance. But the process of testing this null and alternative, only null hypothesis, because alternative hypothesis cannot be tested. Okay, so in the testing of that null hypothesis of there is no difference in the mean values of 3 or more than 3 populations. Okay, it is not as simple as single mean test or the 2 means test. Earlier we have discussed. Okay, so we have to calculate 3 elements for this. Okay, probably all of you have heard and calculated, I hope. So they are called as between treatment estimates, within treatments estimate, and total treatments estimates. So that means another important point which we should have to bear in your mind. In case of single mean test or the single population mean test and the 2 population mean test, the test statistics, earlier we have used the word Z test and T test. And the purpose of this analysis of variance is also same, that is mean test. But the only difference is testing means for 3 or more than 3 populations. So now the question arises in our mind is that, can we continue that T and Z test to compare the means of the 3 populations? The answer is no. We cannot use T test and Z test to test the hypothesis of identical means for 3 or more than 3 populations. One of the reasons for that is, if we use T or Z test, or more specifically T test for that, the implication of that is the level of significance inflated. Level of significance inflated. So that means now you have to compare population 1 mean with 2, 2 with 3, 3 with 1. For example, if you have 3 populations. And every time you have to use T test. And in every test, your level of significance, for example, it is 5% of level of significance. Then 5 plus 3, 5 times 3 is 15%. Actually, you have stated that you are testing your hypothesis of no difference in the mean values of the 3 populations by 5% level of significance, but repeating that test 3 times, your level of significance inflated from 5% to 15%. So, hence, we cannot continue with that T test or the Z test. So Fisher, okay, profound, developed an alternative test to overcome from this problem. So that test is F test. So that is analysis of variance. Hence this analysis of variance, that is, now we are testing the mean values and their equality in terms of the variance, not in terms of the mean values. Because whereas in earlier 2 methods, we have directly tested the difference in the means using the mean themselves. But now in case of analysis of variance, we are testing equality of the means, not based on the mean values, not comparing the mean values, but by comparing the variances of that. So if the variances are differ, the mean is also different. If the variances are not different, So the mean is also expected to be not different. So this is the crux of that analysis of variance. I don't want to get into the theoretical underpinnings. I hope you have already studied that. Otherwise, you better to get into the statistics books of the theoretical underpinnings for this analysis of variance. So hence, we have to calculate two things. Probably that is called in different names. In some books, it is called as between variations, within variations. Here it is called as between treatments and within treatments, and so on. So though the nomenclature, the name is different, but there is not any difference between those words. Between variation means between treatments, within variation here equivalent to within treatments. That's why we have to estimate these two, and we have to compare these variances, estimates using the F test. Earlier I have told you that, and based on this between treatment, within treatment, and other related concepts of analysis of variance, we are able to develop a table based on this, and that is called as analysis of variance table. I hope you are already seeing. So, based on the values of that analysis of variance table, we can finally test our hypothesis, whether we can reject our null hypothesis of no difference in the mean values of the 3 or more than 3 populations, with an alternative hypothesis of at least 2 population mean values are different. And of course, whether I should have to come to or to discuss this, what do you mean by between treatment or within treatment? Okay, I don't want to get into in detail discussion of this. Okay, this is the one between treatment estimate, and we have calculated the mean of that. Hence, it is called as mean square treatment. Mean square treatment. So it is the way in which we comparing or calculating is that we have to calculate the grand mean. Grand mean means, for example, you have 3 populations. You have to calculate the means of mean. Means of mean. The means of mean is called as grand mean, denoted as X double bar. X double bar. Like, for example, you have, okay, 50% selected. That 50% salaries, whether they are identical or not, based on their occupation. So, for example, you are comparing the salary of computer engineer, salary of a mechanical engineer, and one more person. Okay, one more person. Okay, so whether the salaries of these 3 are statistically significant or not, or whether the difference in the salaries of these 3 are significant or not. So that is, since we have 3 groups, mechanical engineer, computer engineer, and one others. So then you have 3 groups, and your purpose is to compare the average salary of these 3 groups. So the between treatment is that because of their occupation, now is you have to call it as a treatment. Occupation is a treatment. That is the variable. Okay, variable. Occupation is a treatment due to because of the treatment. Is there any difference in the mean salary? That is called as between treatment. And within treatment. Within treatment means, within variation means, so the salaries of all computer engineers is not same. There is differences in the salaries of the computer engineers. Then any variations within the group, is called as within treatment or variation within group. So now you have to compare. That is comparing the variation between the group and variation within the group. So if there is, and you should have to take a ratio of these two, one divide one by other, and if these 2 variations are same, then you will get a F value is equal to 1. If the variance between the group is equivalent to the variance of the within the group, the numerator is equal to the value of the denominator, then the F value is 1. So then the 1 indicates that is the value which you obtain, that F is equal to 1, that indicates that, or if your calculated value of the F is closer to 1 means the null hypothesis is true. That means you are unable to reject the do not reject the null hypothesis, or your evidence shows that there is not much difference in the salaries of these 3 types of engineers. If your calculated value of the F is larger, then it is against your null hypothesis, means you are able to reject your null hypothesis. These are the theoretical underpinnings. Then how to calculate this between treatment and mean square treatment, and within treatment and mean square error. That within treatment is also called as error, because of the differences in the salaries within the group, we call it as an error, and we have to take the mean of that. And finally, we have to compare these two. And as earlier I have told you that the F value is MSTR divided by MSC. MSTR means the between treatment variation, between treatment, mean of that should be divided by mean of squared error. Okay, then that gives you a F value. You have to compare this F value with the table F value with respectively the numerator degrees of freedom and the denominator degrees of freedom. And the hypothesis, that is the decision, is as usual. If this computed value by yourself using between treatments and within treatments value greater than the table value, you have to reject your null hypothesis. Otherwise, do not reject your null hypothesis. Just I have told you that. So the same in case of p-value approach also. If your probability value is less than the level of significance, you have to reject your null hypothesis. Otherwise, do not reject your null hypothesis. Okay, and this is the analysis of variance table. I have told you that. Okay, any variation in any variable, okay, is due to because of two things. One is treatment, due to because of error. Treatment means between, because of the error means within the error. If you take the total of these two, that gives you the total error. And generally they are called as SSTRs, SSC, and SST. And you have to have different degrees of freedom for all these three phenomena. If you take the mean values of that, earlier we have noted that MSTR and MSC, and the F is MSTR and MSC. So finally, the last column provide us, okay, the final value for our F test. Okay, with this, let me take one example for this. Okay, the example is related to a company, that is Reed Manufacturing. Janet Reed would like to know if there is any significant difference in the mean number of hours worked per week for the department managers at her 3 manufacturing plants. Okay, so this company has 3 manufacturing plants in Buffalo, Pittsburgh, and Detroit. Whether the average number of hours worked by the managers is same or not. That is the problem. So then for this problem, okay, the null hypothesis is there is no difference in the average number of hours worked by the managers. Alternative hypothesis is at least in one plant, the number of the hours worked by the managers is different. This is the null and alternative hypothesis. And for this, we have to select a simple random sample, means we have to select the managers by making use of this simple random sampling. Let us assume that 5 managers are randomly selected from each 3 plants, and the number of the hours worked by of these 5 managers are collected, and the informations are given in the next table. This is observations are 5 managers. Plant 1, plant 2, and plant 3. The number of the hours worked by the manager 1 in Buffalo plant is 48 hours, 54 by the second manager, 62 hours by the 5th manager. This is the meaning of this 48, 54, and so on. And the same is for the plant 2 and plant 3. And let us assume that we have calculated the required statistics for this. That is, we need mean value. So hence the mean, that is the average hours of work by the managers in first plant is 55 hours, second plant is 68 hours, third plant is 57 hours. This is the difference in the mean hours of working by the managers in 3 plants. So by the outlook, just by observation of the sample mean values, there is a difference, because in second plant, highest number of working hours by the manager 68, whereas in the second and third and the fifth one, it is only 50.57. But you cannot just come to conclude here is that since there is a difference in the number of the R's in the sample, there is a significant difference in the population. So that's why this difference might be because of a chance. So another important point which you should have to bear in your mind in hypothesis testing, or the whole process of hypothesis testing, is to answer for only one question. That is the difference which you have been observed in your sample, whether it is real or due to because of a chance. If it is real means, yes, the difference which you have observed in your sample values is true. And the chance means not true. It is because of the chance means the sample observations which you have selected for your analysis possesses such a characteristic of no difference. Hence, it might be a chance. So that's why, irrespective of your hypothesis testing, not just here, wherever you test, irrespective of the statistical tools. So your theme of that hypothesis testing is to answer for only this question, whether the difference which you have been observed in your sample is of a real difference or a chance. Hence, though you have been observed here, there is a difference of the number of the average hours of working by the managers, but you cannot just conclude here, or you cannot make any decisions at this stage, because whether this difference is real or a chance. So for that, we have to do or to conduct this analysis of variance in this case. And one more phenomenon which we have needed is sample variance. That is the variance in each plant in the number of the hours of working, that is 26.5 and 24. These are the fundamental statistical tools which we are required to do the further analysis of this hypothesis testing. And as earlier I have told you that this is our null and alternative hypothesis. And again, as the process earlier I have told you that after that you should have to state or to specify your level of significance. Here we have chosen 5% level of significance. Then we should have to compute all those earlier statistics. That is, we have to compute between treatments and its mean value, within treatments at mean value, and then how to calculate the between treatments and the mean square of the between treatment. Earlier we have noted that it is x bar minus x double bar. How to get that x double bar? In the previous slide, you have noted that the average hours of work by the managers, 3 managers, are this divided by 3. That is the mean of the mean. This is the average hour of hours per week by all the managers, all 15 managers, for example. So that is 60. And you should have to take the difference between these two. First plant average with grand mean, second plant average with grand mean, and so on. You have to square the difference, multiply it by the number of the observations, and that gives you 490 divided by the degrees of freedom. For this is 2 minus 1. Here, sorry, 3 minus 1. 3 means you have 3 groups. You have to plant 1, plant 2, and plant 3 minus 1. That's why 490 divided by 2 is 245. 245. Okay, this is the mean square due to treatment. Similarly, mean square due to error is calculated by in this way. Okay, that is equivalent to 25.66. Then you have to get a f value from these two values, 245 by 2.25 points, so on. Then the value is, answer is 9.55. This is your calculated value. So now you have to use this calculated value and compare it with the table value. Okay, the table value. So the table value for this problem is f that is f is equal to 6.93. 6.93. Okay, this is for probability value. Okay, and since it is a probability value approach they have given, of course. Okay, that is even it is f is equal to 6.93. But whereas our calculated value is 9.55. This is the calculated value of f. The table value of f is 6.93 at 1% level. Okay, so this is less than our calculated value of 9.55. So hence we have to reject our null hypothesis. So that's why the conclusion of our discussion here is that we can reject our null hypothesis at 5% level of significance, because we have a sufficient evidence to conclude that the mean or the average number of hours worked by these the managers in these 3 plants per week, okay, is not same in all the 3 plants. Okay, there is a difference in which plant the number of the hours of the work the managers worked more, or in which plant the average number of the hours worked by the manager is less. We are unable to answer for this question by using this analysis of variance. So hence statisticians have proposed and extended this analysis of variance with a concept called, with a tool called post hoc test. So the in case of that post hoc test, we are able to compare first plant with second plant with third plant with first plant. So by comparing that, we are able to answer for that. So that's why if you want to make use of this analysis of variance for your analysis or your study, you don't forget to use that post hoc analysis. By that post hoc analysis, you can get some further information, and in such a case, you can suggest your policies more say accurately than just relied on the results of this analysis of variance. So this is about the analysis of variance. Okay, these are the 3 fundamental parametric tests we have been discussing thus far from last almost 2 hours, almost more than 2 hours. Okay, 2 hours, and we can continue this kind of parametric test, not to test the mean values in this form, and also we can continue to test the variance. We can continue to test the proportions, and even we can continue to test the variances by using this parametric test. And further, we can also make use of this parametric test in correlation analysis, in regression analysis, and also in other statistical tools, like in your canonical correlation, and also in your other kind of test like conjoint analysis, and so on. Okay, but this is a fundamental kind of test that make uses of the parametric related procedure for testing hypothesis. So then now let me take a brief discussion on the non-parametric test. Non-parametric test, because there are equivalent number of non-parametric tests. So again, since we have only another 45 minutes to end our discussion, okay, and for that another 15 minutes needed for our discussions. So I had another only half an hour. So just my discussion related to this parametric test is to introduce the different kinds of non-parametric tests. Okay, so the most important non-parametric tests, and their names are as follows: sign test, Wilcoxon signed rank test, Mann-Whitney Wilcoxon test, Kruskal-Wallis test, rank correlation test. So these are the few important, okay, non-parametric test. So as already we have noted that these tests are used in the context of your collected data or the information, or generally your variables are nominal and ordinal variables. If they are nominal and ordinal variables, then you should have to use these non-parametric tests based on, so whether you are testing only one population and comparing the 2 populations, or comparing 2 populations with independent in nature or dependent or matched pairs, or even comparing the 3 populations or more than 3 populations. So for that, earlier we have used T test, Z test, and F test. Equivalently, in case of non-parametric test, we have these different tests. So earlier already we have noted these things, since we need not to get into this. Okay, among this, the first one is sign test. Sign. So this test is a common test which involves using the sample of n potential variable. Here the customers, for example, to identify a preference of 1 to one of the two brands of a product. So it is related.
Sir, excuse me, sir. Sir,
Yes,
sorry
yes.
for disturbing.
Yes, yes.
Sir, actually, your screen is not visible, sir.
Oh, okay. Probably I have get into first share. Huh?
Yes, sir.
Yes. Non-parametric. Sure.
Yeah, now it is visible, sir.
Oh, no, it is old one. It is old one. Okay, I have to use also this. Okay. So I hope now it is visible.
Yes, sir. Non-parametric tests.
Yeah,
yes,
yeah.
sir. It is visible. Sir.
Okay. Among this, the first one is sign test. So now we have taken again example related to customers. Okay, marketing analysis. Okay, here the purpose is to test the preference of the customers between the two products. Why the customers prefer one product to the another product. So then here the preference is a perception of the customer which cannot be measured. Okay, I hope you got this idea. Okay, now we are measuring the preference of the customers for the product. For our simplicity, we have taken only two products. Okay, the customer, for example, customer 1 prefer A over B. Maybe the fifth customer prefer B product over the A product. So hence, you are measuring the preference of the customer. The preference is not a continuous variable. Preference cannot be numerically measurable, like your price, demand, dividend yield, or production, so on. Hence, preference is a nominal variable. We have to use sign test in comparing the preferences of the customers. Okay, then just I have told you that the objective in case of this sign test is to determine whether there is a difference in the preference of the customers between the two items. Here, the two products being compared. The preference, the perception of the customers, is there any difference in that or not? Okay, so for that purpose, what we should have to do in practice, you should have to record the preference data of those two customers. That is whether the customer prefers A or prefers B. And in case of this recording the preference of the customers, you have to use the sign. The signs are nothing but plus and minus sign. So you have to use that plus sign if the individual prefers one brand, and minus if the individual prefers the other brand. Okay, so now we are 50%. Let us assume that the first person prefers the A bond, A1, but the other person not prefers A, means you have to put minus sign for him. Whereas the A, since he prefers, the first consumer prefers A, then you put plus. That's why the preferences are recorded, represented in terms of the signs, plus and minus. Because of this reason, this name of the test is sign test. Sign test. Just I have told you that. So hence here, of course, there are some conditions. The condition is that this is a small sample test. Okay, if the number of the observations, sample size is less than or equal to 20, you have to use this sign test. And the hypothesis for this sign test, as already noted, that there is no preference for one brand over the other exists. The alternative hypothesis is that a preference of one brand over the other exists. That is, there is a difference in the preference is an alternative hypothesis. There is no difference in the preference of the customers between the brands is the null hypothesis. Okay, and in symbolically, they are represented the preference like this. They are in terms of the preference. So the proportions. So proportion is equal to 0.5. So 0.5 means equally 50% of your selected sample prefers one, The remaining 50% are preferring other one. Hence, there is no difference in the preference. So if there is a difference means your proportion is not equal to 50. That means 70% of the persons preferring a brand, remaining 30% are percent of the persons are or the customers are preferring the another brand. So that is why it is an alternative hypothesis. That is the meaning of 0.5 equal in the null hypothesis, not equal in the alternative hypothesis. And the next procedure is the number of the plus sign is to our test statistics. So out of this plus and minus one, which sign we should have to count here? Used here, we have to use only plus signs. And assuming the null hypothesis is true, that is no preference, no difference in the preference. Simply the sampling distribution of this test is a binomial distribution. I hope many of you have also knew about these kinds of tests. Okay, they are based on discrete type of variables: binomial distribution, Poisson distribution, binomial Poisson distributions. They are all the discrete types of distributions. Whereas F test, whereas the T test, Z test, they are called as the continuous distribution, including the chi-square test. They are the continuous distributions. That's why the binomial distribution is a discrete distribution with a probability of 0.5. So then we can here also use the p-value. If the p-value is less than your assumed level of alpha, you have to reject our null hypothesis. Okay, and of course, here even in case of this sign test, that is the large sample test. Okay, that is the large sample test. Whereas in case of small sample test of sign, whereas in case of the large sample test, the number of the observations you have selected are greater than 20. Here also you have to use that plus signs as your observations, and since the number of the observations are greater than 20, approximately that follows the normal distribution, and hence we have to use the two things earlier we have noted in the parameters, like the mean and standard deviation, but the mean and standard deviations are distinctly different in the way they are used in this case of non-parametric test in general, including this sign test. The mean is 0.50 n. That is the number of the observations should be multiplied with this probability of that. That is the mean is 0.5, and the standard deviation is the square root of 0.5 times the n. Okay, so then by using this mean and the standard deviation values to calculate our mean and standard deviation, again we use our old Z test. That is the Z is equal to x minus mu divided by sigma, and here the x represent only the number of the plus signs. This is the process in case of the sign test for the large sample. So now we have an example for this. So it is related to again marketing research. Okay, a sample of 36 customers were asked to taste 2 brands of ketchup and indicate their preference. That is the brand A and brand B. Do the data shown on the next slide indicate the significant difference in the preference of the consumers between the 2 brands? We need to answer for this. And here 18 customers prefer brand A ketchup. We have assigned them a plus sign for them, or we have recorded with the plus sign. Whereas the 12 customers preferred brand B, and we have recorded their preference with the negative sign. But there are 6 persons in our customers, okay, customers of 36 have no preference. Hence, you should have to omit that no preference related customers from your analysis. Okay, and now your analysis is based on only on the plus sign. Hence, the analysis will be based on a sample size of 18 plus 12, that is 36. Though your original sample size is 36, but for your analysis, for your calculation, you should have to take only 30 observations. Then the hypothesis null and alternatives are no preference of one brand over the other brand that exists, and there is a difference or a preference by the customers of one brand over the other brand exists. So that is the alternative hypothesis. Then this is the diagrammatical representation and the calculation. That's why here the how do you have to calculate that mean and the standard deviation? The mean formula is 0.5 into n. N is 30. 0.5 n is 50. Then standard deviation is 0.525 n square root. Then 0.525 into 30, the square root for that gives you 2.74. That's why the standard deviation value for this problem is 2.74 and the mean value is 15. Why it is 15? Because there are 30%. So if equally 15 and 15% are equally prefers, no difference in the preference. So that's why the 15 comes here. Okay, and the standard deviation based on that. Okay, so by using this calculated values, the mean and the standard deviation, you have to substitute out our Z formula x minus x bar by standard deviation. Your calculated value of the Z statistics is 1.10, and the probability value is calculated like this by using the probability value given in the Z table. Okay, for 1.10 it is 0.3646 and subtract it from 0.5 and multiply this difference by 2, that gives you 0.27. This is the 0.27. 0.27 is the probability value. Then the conclusion is your testing hypothesis at 5% level, but the probability value is 27%. Since it is greater than your probably the level of significance, hence you cannot reject your null hypothesis. So, or in other words, the usual hypothesis testing procedure also follows in case of this sign test of large sample. If the here in this example, probability value is probability value is 0.27, but the your hypothesis or the chosen level of significance is 0.05. Hence, your probability value is greater than your chosen level of alpha of 5%. Even at 10% you can take. We cannot reject your null hypothesis. That means there is insufficient evidence in the sample to conclude that the difference in preference exists for the two brands of ketchup. That's why there is no difference in the preference of the customers regarding A brand and B brand. So this is the way you can test. So that is, you can use this sign test to check the preference or any satisfaction level or any such qualitative nominal variables. Preference is a nominal variable. Wherever you have a nominal variable regarding the preference, regarding the their prescript, that their perceptions, generally that is the perception. Wherever you have a perception of the variables, the perception kinds of variables are the nominal variables. They can be tested by using these types of test, sign test. Okay, then one more, the median. Okay, when I started my discussion in the previous session, I have told you that the appropriate type of central tendency for the nominal or ordinal variables, are more specifically related to the ordinal variable, is median. So hence we can use that median and test that median regarding whether there is a sign, a difference or not. Okay, here we can use that signs to the medians. We can test, which is of course a continuation of that sign test. By instead of using signs, we are using the medians for that signs. Okay, medians for that signs. So related to one example, fitness, trim fitness center intent to test are being conducted about the median age of the members, more specifically female members of that fitness center. So they assume or hypothesize that the median age of female members is 34 years. The median age is not equal to 34 years is the alternative hypothesis. Though the age is a quantitative variable, but you are taken the median of that. Hence, you cannot use parametric test. So the median is using here. Hence, you are using an unparametric test. Is it called as the median test? So for this purpose, okay, the process again is an example. 40 females have been selected from that. Okay, 25 are older than 34 years, 14 are younger than 34 years, and one is 34. Hence, you have to omit that 34. Okay, one is exactly 34. You have to omit that. As earlier we have noted that, and this is the process. The same formula. That is, the mean is 0.5 into n. The mean, that is the standard deviation is square root of 0.25 n. So these are the calculated values of the mean and the median. standard deviation, we are of course again using the z-test for the median also. And this is 1.76 our calculated value. So the probability value is 0.07. We cannot reject your null hypothesis of the difference in the mean values, the median values of that age of above or below 34. You cannot reject it at 5% level, but you can reject at 10% level because the probability value is 0.7. So this is a median test. And the next one is Wilcoxon signed rank test. Okay. So this is also a non-parametric test. And this is a alternative test to the matched pair test in parametric sample. That is, earlier we have used Z test for matched pairs, T test for matched pairs for dependent two variables. So if your variables are qualitative, if your variables are ordinals, so in such a situation, you have to use this counterpart of the matched pair test, namely Wilcoxon signed rank test. So it is also a sign. The ranks are assigned to that signs and compare the two variables in terms of the signs. Hence it is called as signed rank test, developed by a statistician called as Wilcoxon, and hence it is called as Wilcoxon signed rank test. And in case of our earlier parametric matched sample test, what we were did, or what it was required, it was an interval variable. That is the quantitative variables. There we were compared the differences of the pairs of that interval variable, which were assumed to be follow normal distribution. So if that normal distribution is not satisfied, not approved, then the Wilcoxon rank test as Wilcoxon signed rank test has been used even for the interval variables, not just for ordinal or the nominal variable. That is the point which you should have to bear in your mind. So now let us consider one example for this, for a company where it has an express deliveries. Okay, a firm has to decide to select one out of two express delivery services to provide next day deliveries to its district offices. That is the services for the district level for a firm. So to test the delivery times taken by these two services, okay, the firm sent two reports to a sample of 10 districts offices, with one report carried by one service and the other report carried by the second service. And now the question is, do the data on the next slide related to that services, time taken by that services to provide services to that district level officers, okay, indicates any difference in the two services. Okay, this is the number of hours taken by the two services. The one name is overnight service, the other one is night flight service. Okay, so these are the two companies. The numerical values are the hours taken by these companies to serve these districts. For example, the overnight take 32 hours to reach that Seattle, whereas 25 hours by the night flight. So likewise, there is a difference in the services of these two companies. So then it has to decide whether to select overnight company or the night flight company to provide services at the district level by this particular firm. So for this purpose, we can make use Wilcoxon signed rank test. And what is the steps involved to do this Wilcoxon signed rank test are as follows. First, we should have to compute the difference between the paired observations as usual in the earlier case. Discard any observations or the differences with zero values. Then rank the absolute value of the differences from lowest to highest. Tied differences are assigned the average ranking of their positions. For example, in case of Spearman rank, probably you have calculated, solved in your statistics classes, like tied ranks. The same procedure also used for the tied rank here also. Given the rank signs of the original difference in the data, and you have to sum all those signed rank. And next we will have to determine whether the sum is significantly different from zero or not. So related to our example, so this is the difference between the time taken by the two services for the Seattle. So for Seattle, the 7 hours differs in the number of hours taken by them. And we have to rank these differences. This is the rank 1.5 because 1, if these are the highest values or the lowest values, ascending or descending order. So since equal value, you have to, since they are tiled ranks, they are equally divided. So then sign rank means, so you have to assign all plus for plus values, minus for minus values, and the total is 44. Okay, total is 44. This is the sum of the sign ranks. Okay, using this sign rank, now you are able to test using this formula. This is the formula to calculate, okay, the mu t, that is, there is no difference in the services time taken, whereas the standard deviation is calculated from this. So n into n plus 1 times n 2 times of n plus 1 divided by 6. So here 10 is, we have 10 values of plus, then 11, 10 plus 1 is 11, and it is 20 plus 1 is 21. Okay, if you just simplify it, this is the standard deviation. The standard deviation of this problem is 19.62 and the mean value is 0. And we have to use a Z test here also, but the notations are different. T minus mu t. T is the sum of the ranked values, 44, I hope you remember in the previous slides. And minus 0, because we are assumed there is no difference in the service time taken by these two services. That's why 44 minus 0 divided by the standard deviation, 19.62. 44 divided by 19.62 is 2.24, and the probability value is 0.25. And of course, it is 2.24 is greater than 1.96 of the probability value of a table in Z test. Hence, we can reject the null hypothesis of no difference in the hours taken by these two services. Means there is a difference, okay, in these two companies in terms of the services they are providing, in terms of the number of hours to reach these, say, 10 cities. So hence, the final decision is, the decision taken by the company is that the firm has to select a company which provide the service with the lesser number of hours. That is the policy decision. So hence, the Wilcoxon signed rank test is an equivalent test to your matched pair in case of parametric test, or it is a counterpart of parametric matched pair test. So this is about the Wilcoxon rank test. And the Mann-Whitney-Wilcoxon test, this is also a non-parametric test, but this test is used to identify the difference between the two populations, whereas the earlier was also used for two populations for the matched pair, but the Mann-Whitney-Wilcoxon test is used for the difference between the two populations. And Wilcoxon signed rank test, earlier we have not noted that it was based on the ranks, but this, unlike this, is not based on this rank, but this requires the interval data or assumptions of both populations are normally distributed. The only requirement for this is the measurement scale is at least ordinal. But whereas that Wilcoxon rank sign test can also be used for that that nominal type of data also, because there you are representing in terms of the ranks. But whereas this is purely the ordinal one. Okay, only for ordinal types of data, if you want to compare the differences in the mean values of the ordinal variables, you can use this Mann-Whitney or MWW test or Mann-Whitney Wilcoxon test. Okay, and this is the procedure, we need not get into that. Okay, this is the Mann-Whitney test, and this is for example, it is related to the energy cost of the two types of freezers. Western freezers, eastern freezers, whether is there any difference in the energy cost of these two. So we can compare the differences between these two variables, that is between the two companies freezers, using this Mann-Whitney Wilcoxon test. That is for small sample. You can also do this for the large sample case when the formulas are like this. And in both of these two cases, one of the important points which you should have to bear in your mind, Whereas in case of the independent sample test, there we have used t test and the z test, but there we have taken the differences and directly we have used the differences in our formula. But whereas in case of this Mann-Whitney-Wilcoxon test, we have identified the differences, and the differences here they are ranked. Here the values are ranked, not in case of the parametric test. Okay, in case of this Mann-Whitney-Wilcoxon test, the values are ranked. So hence there is a difference in the methodology of estimation. And these are the formulas. So the mu is like this. The mean value is 1/2 times of, this is the number of the observations, n1 and n2. Okay, and we have to simplify this. And the standard deviation is calculated by this formula. And we have to use these two again to the same earlier formula. Z is equal to t minus mu t divided by the standard deviation. And we have to simplify this. Since the probability value is 0.16 greater than even 10% level, we cannot reject our null hypothesis. That means there is no difference in the energy cost between the two freezers. So the energy cost of those two freezers are one and the same. And hence, as a company or as a household, you can select any refrigerator or the freezer for your purpose. So that is the policy implications related to this. Okay, then the fourth one is the Kruskal-Wallis test. So this KW test or Kruskal-Wallis test is equivalent to your analysis of variance. Equivalent to your analysis of variance for continuous data, but this Kruskal-Wallis test is used for ordinal type of data. Or you can also use interval variables for this Kruskal-Wallis if your normality assumption is violated. But if your variable is ordinal, then you should or you must have to use this Kruskal-Wallis test. Kruskal-Wallis test. So that's why the Kruskal-Wallis test is a test of testing the difference for 3 or more than 3 populations, which is a counterpart of your analysis of variance. And your variables should be ordinal in nature. That is the condition to use this Kruskal-Wallis test, and the formula is somehow complex like this. So here the K number represent the number of the population, I and NT represent the number of the items in the sample, I, the total number of the items in all the samples, and it is the ranks. That is another important point. In all these non-parametric tests, I hope you have been observed that, okay, though they are represented in quantitative way, so they are ranked. Only the ranks of the selected variables or the variables are converted into ranks, whether it is in sign case, whether it is in other cases, ordinal cases, all them are converted or transformed into ranks only by using the ranks. So the formula, that is the values are the critical, that is the calculated values are calculated. So this is related to this, and whereas this Kruskal-Wallis test follows the chi-square distribution. The earlier test, sign test in the large sample case, then the KWW test, okay, for the matched square, they follows the normal distribution. But this Kruskal-Wallis test for testing the equality of the differences of 3 or more than 3 populations follows the chi-square distribution. Hence, we should have to use chi-square distribution related analysis. The last but not the least, which is known to everybody, I hope, that is the rank correlation. It is also a non-parametric test. We can use this non-parametric test to test our hypothesis. And in case of a rank correlation, as all of you are noted that, which has been used again for the ordinal type of data. Okay, so here our purpose here is to measure or to identify the difference between the ranks of the 2 ordinal variables. You have to rank them. You have to take a difference between the ranks, and you have to use the formula, that is 1 minus 6 sigma d square divided by n into n square minus 1 formula. And by using this, you can test your hypothesis whether there is a difference in the 2 populations or not using this rank correlations. That's why there is no rank correlation exists, and there is an existence of the rank correlation among your ordinal variables or association. The association kind of test can be tested by using this rank correlation for ordinal type of data, whereas for continuous or quantitative data of data, okay, that is Pearson coefficient of correlation has been used. I hope you have known it from your statistics. class. Okay, this is about that rank correlation. So I don't want to get into this because you know the way of calculation of this rank correlation, but we use that Z once again here. The user estimated calculation of the rank value is used here and divided by its the denominator. And if that value is greater than the table Z value, or if the probability value is less than your chosen level of alpha, you have to reject your null hypothesis. Otherwise, do not reject your null hypothesis. Okay, this is about the rank correlation. So under this non-parametric test, thus far we were discussed briefly about sign test. So then Wilcoxon sign rank test and the KWW test, and then Mann-Whitney test, and Mann-Whitney Wilcoxon test, and the rank test. Okay, so these are the few non-parametric tests where we have to use these tests in the context of if our variables are nominal variables, if our variables are ordinal variables. So even if we can make use these types of non-parametric tests for the continuous variables, if the normality assumption is violated. So with this, I conclude related to the non-parametric test, and one which is widely used non-parametric test, of course not included in this part because that is a test which is along with the parametric test normally that has been given in the statistics books. Though it is a non-parametric test, there is the chi-square test. So the chi-square test is also a non-parametric test. So I hope okay, all of you have so familiar with that chi-square test. Okay, chi-square test. So if I take that chi-square test, for example, the chi-square test has been used for different purposes. So that the one most important purpose of use of that chi-square is to measure association, measure independence. So that means your variables are either ordinal variables, either if they are nominal variables. So in both of these two cases, whether your variables are nominal variables, whether your variables are ordinal variables, in all those cases, if you want to find any association between these nominal and ordinal variables, if one is ordinal, other one is nominal, even in such case also you can use this chi-square test. And along with this test of independence as one of the purpose of use of this chi-square test, the other one is goodness of fit of data. Whether you can also we can test or we can use this chi-square test as a goodness of fit. That means you have some expected values, and whether that expected values can be accepted or not based on observed values. So that is called as goodness of fit type of data. So out of this, okay, the most important and widely used.
Excuse me, sir.
Yes, sir.
Sir, actually the screen is not visible.
Not visible. Okay, not visible. Okay. 1 minute. Close this first. Yeah. So Chetan, now I hope it is visible.
Chi-square test. Yes, sir, it's visible.
So this, okay, there are two important purposes of use of this chi-square test. Just I have told you that one is to test the goodness of fit. The second one is to test the association between the nominal and ordinal variables, or among ordinal variables, among nominal variables, or between two or more ordinal and nominal variables. So that is called as test of independence or test of association. The other one is goodness of fit. The third one is the test of homogeneity. So whether our data which have been collected from for a variable which follows the normal distribution or not. So we can also use this chi-square test for that. That is called as test of homogeneity. But out of all these three, the most popular, widely used in practice, is the chi-square test for measuring association between the nominal and ordinal variables or among ordinal and nominal variables, and which is called as test of independence. So now I have taken just a few minutes for this, okay, for the test of association. This test of association is also called as the test for contingency table. Okay, that is normally we make use this because this chi-square test of association, chi-square test of independence, chi-square test for this purpose make use as contingency tables. Hence, it is also called as chi-square test to a contingency table. And as just I have told you that this test is this contingency test or the test of independence, test of association is used to test whether the two nominal variables are related or not, or there are differences between the two or more populations of nominal variables or not. Both for association and also for the difference, we can make use this contingency tables related chi-square test. To accomplish these objectives, we need to classify our data into two different criteria. That's why you should have to classify your variable into at least two classifications. Okay, classifications. For example, is there any difference or is there any relationship between education level and their participation? Education level and their income, if the income is measured in ordinal form, and their gender and the level of education, gender and income, gender and preference. Like this, we can quote several such examples. And of course, the quoted or just stated variables are either nominal variables or ordinal variables. So hence, you should have to divide your selected variable into two different criteria, two different categories or group. That is the one important condition to use this one. So now here we have an example. The example here is related to an effort to better predict the demand for courses offered by certain MBA program. It was hypothesized that the students' academic background affect their choices of MBA majors, thus their courses selection. So this is related to an education-related research, or of course by an institution, MBA-related program offered institution. So what made the students to select the MBA program? Because in MBA program there are different programs. That is the major. Okay, that is accounting major, finance major, marketing major. So in selection of accounting, in selection of finance as a major, or in selection of marketing as a major, or even in selection of a human resource development as a major in MBA, or any other such MBA selection, whether their undergraduate degree influences on the selection of their preference or not. So hence, here the preference of the MBA graduates in selection of major accounting MBA, finance MBA, or marketing MBA influenced by their undergraduate degree. That's why whether their undergraduate degree like BA or BE engineering or BBA or any other degree, because MBA program is offered for any degree students. So hence, whether their undergraduate degree impact or influences on their preferences of selection, the major in management, okay, or MBA program. So this is the problem. Okay, now this is a contingency table. I hope all of you knew that. The two classifications are here. The group criteria are, one is their undergraduate degree, the other criteria is major, MBA major. So the values in the cells provide the preference. 31 BA graduate preferring accounting, 13 financing, and the marketing preferred by only 16 students having BA degree. So that is the way which you should have to interpret, and that is the meaning of those numbers in the different cells. In totally, 60 students of BA are joined to this MBA program, 31 from BE engineering, BBA 60 students, and others are 39. And Out of the total 152 MBA major students, 61 are accounting preferred accounting, 644 are finance, and 47 are marketing. This is the way, and these are all called as observed values. Observed values. And these are observed values are the data which you have collected directly by you regarding their undergraduate degree and their preferences regarding the MBA major. So this is the table you have. So now our purpose here is our hypothesis testing. In case of this is whether their undergraduate degree influences impact on their majoring in MBA. So that is the question we have. Then the solution, of course, I hope all of you have been used this formula to calculate this chi-square test. This is the chi-square, which is equal to sum of the values of your observations from I1 to K. Here F represent the observed values or observed frequency. E refers to expected frequency. So you have to calculate expected frequency from the observed frequency. You should have to take the difference between these two. You have to square that difference and divide that difference by the expected frequency. Then you have to sum all these values. Finally, you will get a chi-square value, calculated chi-square value. So then you have to use this calculated chi-square value and compare with the table chi-square value. Again, the decision is as usual. If your calculated chi-square value is greater than the table value, reject your null hypothesis. Otherwise, do not reject your null hypothesis. That is the point given under this rejection reason for the degrees of freedom, respectively, for the row and columns with less 1 in case of these degrees of freedom. So this is then now to calculate this expected frequency. You have to use this. I don't want to get into that. So probably the simple way of calculated is that it is raw total multiplied by column total divided by total, grand total. Probably you remember these words. So for calculation of every cell, filling every cell of this expected frequency, the formula is raw total multiplied by column total, then divided by the grand total. So by using that, you are able to fill all these. So all these. So then that is just I have told you that raw total, column total divided by sample size or nothing but the grand total. So just we have interpreted like this. Actual or the observed frequency is 31, expected frequency is 24.04. So how we have derived? We have derived like this. So that means we have multiplied the column total with the raw total divided by the sample size or the grand total. That gives you 24.08 for the first one. That is observed is 31. That is out of 151 students having BA degree opted accounting. That is the meaning of 31. But expected one is that based on this information, actually only 24 should be expected, not 31. There is a difference. Whether this difference is statistically significant or not, for every cell, we should have to do manually all those things in these calculations. And finally, we will get sum of all these squares, their differences, squares and summations, and so on. Finally, you will get a calculated value of 14.7. Okay, this is the calculated value of the chi-square. This calculated value of the chi-square should be compared with the table value. So the table value is 12.59. Since your calculated value of 14.70 is greater than the table value or the critical value of 12.59 at 5% level, so there is a sufficient evidence to reject your null hypothesis. That means that they are dependent. That means their undergraduate courses influences on majoring in MBA. Selection of auditing, selection of financing, selection of say marketing as major, they are influenced by their undergraduation. That is the policy aspect or the conclusion. So like this, you can use this contingency table wherever or in all the context where your variables are nominal in nature, because it is the two are the nominal variables. One is their undergraduate degree is a nominal variable, their selection of major in MBA is also a nominal variable. So that's why whether these two nominal variables are dependent or not, whether the undergraduate degree impact on the selection of the major in MBA degree. So you can interpret in both these two ways. Dependent means there is an influence. And as earlier I have told you that your variables always need not to be a nominal variables for this purpose. Even for ordinal variables, you can use one variable is ordinal, other one is also ordinal. You can also use one is nominal, other one is ordinal. You can use this contingency table method or test of independence or a association by using this chi-square test. Chi-square test. That's why till the date, though you or we have all that sign test, sign rank test, MW test, KWW test, and so on in non-parametric types. Till the date, the most popular is this contingency table related analysis or simply chi-square test. That's why if you get into most of the statistical tools or the applications of statistical tools for nominal and ordinal variables or non-parametric test related analysis, so the chi-square test is widely used because it is so simple. By using just this cross tabulation analysis, we are able to test our hypothesis. Okay, with these words, so this is a brief discussion on this chi-square test as one of the popular and widely used non-parametric test. So with these words, I conclude my discussion related to parametric and non-parametric test in another 2 or 3 minutes. Okay, so we have started with the selection or choosing appropriate.
Sir, please unmute yourself, sir.
Okay. So we have started our discussion with the selection of an appropriate statistical tool for our research work, data analysis more specifically. In that, which tool, which statistical technique we have to select based on our research question, based on our hypothesis. Once that is identified, decided, the next one is the number of the variables we have selected in our hypothesis, whether it is for comparing the difference, measuring the association, measuring the impact of the variables. There we should have to decide. That is the number of the variables. And once we have decided the number of the variables, then we should have to rely on univariate, bivariate, and multivariate statistical tools. And once we have decided or determined the number of the variables and selected the appropriate statistical tools of univariate, bivariate, and multivariate, the next one is we have to determine the measurement scale. That means whether our variable is a nominal, ordinal, interval, or a scale variable. After that, whether you are using these statistical tools for descriptive purpose or inferential purpose. If it is for descriptive purpose, you need not to say test a hypothesis there. You need not to have parametric or non-parametric test of hypothesis in case of descriptive purpose. So if your purpose is to infer about the population based on the sample evidences, then we have parametric and non-parametric tests. And under that discussion of parametric classifications, of course, we have just taken only one statistical parameter, that is the mean as a parameter. So, and for that mean as a parameter, we have used some tests of parameters like single mean test, 2 means test, 3 or more than 3 mean test. For this purpose, we have used t-test, z-test both for 1 mean and 2 means, and f-test or analysis of variance for 3 or more than 3 mean test. So similarly, we can test other population parameters like proportions, like variance as the parameters of the population. And in case of the non-parametric tests, we have been discussed in brief about the non-parametric tests, which are the tests only used for nominal or ordinal types of data. We have equivalent or counterparts of the parametric tests for non-parametric tests for non-parametric tests. So that means so we have a paired matched test in parametric test, equivalent in case of non-parametric test. We have an ANOVA, equivalent test in non-parametric test, and so on. We have been discussed. And among the non-parametric test, as all of us knew that the most popular and widely used is a chi-square test. Okay, this chi-square test is a simple test where we can use this test more specifically for measuring the association, measuring the relationship, measuring the impact among the nominal variables and also among the ordinal variables. So these for the simple statistical tools, because I'm not even able with the stipulated time period getting to the advanced parametric and non-parametric tests, especially parametric test, as Chetan mentioned. Okay, we have econometric tools. Most of those econometric tools are parametric tools, parametric techniques, and we have simple regression, multiple regression, the distributed lag models, then dynamic econometric models, then simultaneous equation models. So then we have logit model, probit models, and so on in econometrics, and almost all those models are parametric type of models. But all the purpose of all those models are not just to measure the relationship, not to just to compare the mean values or so on, but their purpose is to measure the cause and effect type of relationship. Hence, of course, I am not taken them my discussion here because they are of course an advanced kind of parametric type of test. So with these words, I conclude, and I thank all of you for your patience listening from almost more than 3 hours. So now the time is okay. This time is for answering your queries or questions. You are free to ask me any questions or clarifications which you are needed from my side.
The participants can unmute themselves, and if you have any queries, you can raise the same to the professor. If any of the participants have any queries, you can raise the same to the professor. You can unmute yourself. Anyway, sir, I basically have some questions, sir.
Yes, sir.
Sir, actually, while using this chi-square test, there is this, I think there is a rule that in every cell, the minimum observations must be at least 5. Yeah, at least 5. And sometimes when we are actually doing this tabulation and all that, sometimes when we actually enter the value, sometimes it will not be 5, sometimes even it will be less than 5. Now in that context, I personally actually go for Fisher's exact value. So now my first question, sir, is using this Fisher's exact value, does it serve the same purpose without any drawbacks as using chi-square test? This is my first question.
Yes.
And my second question is, if in the cell, if the values is less than 5, then there is one alternative measure. We can actually go for Yates correction factor.
Yes.
Now, in that context, my second question is, are there any softwares wherein I can use this Yates correction factor on chi-square test? These are my 2 questions, sir.
Okay. So you are rightly mentioned that in some situations, the value in some particular cells of our chi-square or contingency table are less than 5, then the results are not reliable. In that cases, we should have to correct it. So one of the correction is by Friedman, as you already told you that, then we have to use the Friedman correction test for that. Okay, then it is reliable. So since that automatically corrects that problem, then we can go for that. And the Yates correction is also the alternative to that Friedman's one. But to my knowledge, you will get the Friedman test for that. But Yates correction is not given by the statistical packages, or they might have, but directly I have not been observed in the output which I have taken for contingency related tables. Because if I get a results for a contingency table, normally we have the values like Pearson's value, then likelihood value, then Kramer's V value. Okay, Kramer's V value. So only we have these types, but the height value is not the height's correction value is not given in the statistical packages. So we will have to look into that. So exactly, I don't know whether it is directly given by the statistical packages or not. Chetan.
Okay, sir. So, and one more question, sir. Sir, actually, this t-test is actually used for only univariate series, is it, sir? Like only univariate series, only one series?
No, need not. Because
when we actually go
even for two variables, that is two sample t-test, there also we were noted that we have used
paired t-test.
Yeah, paired t-test. One in case of one single population or two population, one variable, two variable for mean test, we can use t-test, but not more than two. That is more than three, we cannot use t-test or z-test.
Not more than three or not more than two, sir?
Three or more than three. They are one and the same. Not more than two means three or more than three.
Okay, sir. So thing is, when we are actually using t-test, we should invariably use only for quantitative variables, right, sir?
Yeah, right.
Okay, that is one thing.
Yeah.
And the second thing is when we actually go for this F-test thing. Yes, sir. F-test thing. And when we are actually going for F-test, like we can go for three or more than three, right, sir?
Yes. For me,
three or more than three.
For testing means.
For testing means.
Yeah.
Now here, while I'm actually going for F-test,
okay,
I can use quantitative as well as qualitative, right, sir?
No. Only because F-test is a test of continuous variable. Okay.
Okay, sir.
So hence you cannot use F-test for a qualitative variables. F-test is only for continuous or numerical type of variables. And one more thing is another important point. All of us bear in our mind is that the tests are used for different purposes. Out of all those purposes, I have taken only one purpose, that is testing mean by using t-test, because the t-test is also used in correlation testing, whether the correlation which you have estimated is statistically significant or not. Whether in case of regression analysis also we use t-test, that is a t-test. And in regression analysis or in our econometrics, we use also chi-square, we use also F-test, isn't it? So that's why based on our purpose, they are used for different purposes. But the t-test, z-test and F-test are used only for the continuous variables, metric variables, quantitative variables. Wherever you use, for whichever the purpose you use, that is the basic condition.
Yeah, fine, sir. Yeah, thank you very much, sir. Those were the clarifications.
Welcome. Okay, is there any questions from other participants?
Yeah, the participants can just unmute yourself and raise the question. Otherwise, even you can type in chat box also. So, yeah, I don't think from participants there are any questions, sir.
Okay.
But nonetheless, on behalf of Department of Studies and Economics as well as Research Scholars Forum, as well as on behalf of the participants as well, we wholeheartedly thank you for the systematic and for the wonderful and in-depth analysis and the way you actually threw light on all the parametric as well as non-parametric tests despite your busy schedule. And it was a very wonderful, detailed, example-enriched, practically relevant lecture. We wholeheartedly, truly appreciate all your efforts. Thank you very much, sir.
Thank you very much. And whatever I have been discussing from last 3 hours is just a gist of this parametric and non-parametric tests. I am unable to give you the practical experience of this because we can do all these things by making use of some data using the statistical packages. So the most appropriate one for doing this simple kind of hypothesis is SPSS. I hope many of you have knew that how to use that SPSS for all these purposes. Okay, so and further, I am grateful to the Department of Economics of that is the Davangere University, to providing this opportunity to share my little knowledge with the August gathering of this FDP program. And I thankful to all the faculty members and the chairman of the Department of Economics and all the participants for your presence listening. So thank you. Thank you once again.
Thank you very much, sir. And all the participants are requested to reassemble and be online by 2:30 p.m. By 2:30 p.m., we will actually start regression analysis by Professor Niranjan, sir. Thank you very much, sir. We shall be ending the meeting by now, sir. Thank you very much, sir.
Oh, thank you.
And we wish to see all the participants by 2:30 p.m.